Texture feature extraction. Definition. Texture is repetition of patterns of local variation of pixel intensities. Texture feature is a measure method about relationship among the pixels in local area reflecting the changes of image space gray levels. Example. Texture analysis. There are three primary issues in texture analysis: texture classification, texture segmentation, and shape recovery from texture. Texture classification. In texture classification, the problem is identifying the given textured region from a given set of texture classes. The texture analysis algorithm extracts distinguishing features from each region to facilitate classification of such patterns. Texture segmentation. Unlike texture classification, texture segmentation is concerned with automatically determining the boundaries between various textured regions in an image. Both region-based methods and boundary-based methods have attempted to segment textured images. Shape recovery from texture. Image plane variation in the texture properties such as density, size, and orientation of texture primitives are the cues exploited by shapes from texture algorithms. Quantifying the changes in shape of texture element is also useful to determine surface orientation. Techniques for texture extraction. There are various techniques for texture extraction. Texture feature extraction algorithm can be grouped as statistical, geometrical, model-based, signal processing. Statistical methods include local features, gray level of central pixels, average of gray levels in window, median, standard deviation of gray levels, difference of maximum and minimum gray levels, difference between average gray level in small and large windows, Kirsch feature, combined features, Galloway, run length matrix, Harlick, co-occurrence matrix. Geometrical method includes: first, threshold image into binary images of n gray levels. Then calculate statistical features for connected areas. Model-based method includes: these involve building mathematical model to describe textures, Markov random field, fractals 1, fractals 2. Signal processing includes: these methods involve transforming original images using filters and calculating energy of the transformed images. Loss mask, Lenny's, Dobbechi's wavelets, Fourier transform, Gabor filters. Gray level co-occurrence matrix. Gray level co-occurrence matrix, also referred as co-occurrence distribution. It is the most classical second-order statistical method for texture analysis. An image is composed of pixels, each with an intensity. The GLCM is a tabulation of how often different combination of gray levels co-occur in an image or image section. Texture feature calculation use the content of GLCM to give a measure of variation in intensity at the pixel of interest. GLCM texture feature operator produces a virtual variable which present a specified texture calculation on a single beam echogram. Step for virtual variable creation. Quantize the image data. Each sample on echogram is treated as a single image pixel and its value is the intensity of that pixel. These intensities are then further quantized into a specified number of discrete gray levels known as quantization. Create the GLCM. It will be a square matrix n cross n in size, where n is the number of levels specified under quantization. Step for matrix creation are: let S be the sample under consideration for calculation. Let W be the set of samples surrounding sample S which fall within a window centered upon sample S of size specified under window size. Define each element ij of GLCM of sample present in W set as the number of times two samples of intensities I and j occur in specified spatial relationship. The sum of all the element ij of GLCM will be the total number of times the specified spatial relationship occurs in W. Make the GLCM matrix symmetric. Make a transpose copy of GLCM. Add this copy to the GLCM itself. This produces a symmetric matrix in which the relationship I to j is indistinguishable for relationship j to I. Due to summation of all the element I, j of GLCM will now be twice the total number of times the specified spatial relationship occurs in W. Normalize the GLCM. Divide each element by the sum of all the elements. The element of GLCM may now be considered probability of finding the relationship I to j or j to I in W. Calculate the selected feature. This calculation uses only the values in GLCL. For example, energy, entropy, contrast, homogeneity, correlation, shade, or prominence. The sample S is the resulting virtual variable is replaced by the value of this calculated feature. Framework of GLCM. Example for GLCM matrix for an image. Spatial relationship between two pixels. GLCM texture considers the relation between two pixels at a time called the reference and neighbor pixel. In the above illustration, the neighbor pixel is chosen to be the one to the east or right of each reference pixel. This can be expressed as 1, 0 relation, 1 pixel in x direction, 0 pixel in y direction. Each pixel within the window becomes the reference pixel in turn, starting in the upper left corner and proceeding to the lower right. Pixels along the right edge have no right-hand neighbors, so they are not used for this count. How to read the matrix framework. The top left cell will be filled with the number of times the combination 0, 0 occurs. That is how many times within the image area a pixel with gray level 0 fall to the right of another pixel with gray level 0. How to read east matrix. Twice in the test image, the reference pixel is 0 and its east neighbor is also 0. Twice the reference pixel is 0 and its eastern neighbor is 1. 3 times the reference pixel is 2 and its neighbor is also 2. Understanding GLCM more. GLCM represents the distance and angular spatial relationship between over an image subregion of specific region of specific size. The GLCM calculates how often a pixel with gray level value I occur either horizontally, vertically, or diagonally to adjacent pixel with the value j. Direction analysis of GLCM. Horizontal 0 degree, vertical 90 degree, diagonal, bottom left to right top minus 45 degree, top left to bottom right minus 135 degree, denoted by P0, P45, P90 and P135 respectively. Direction analysis of GLCM. GLCM of an image is computed using a displacement vector d defined by its radius delta and orientation theta. Consider a 4x4 image represented by figure 1a with four gray tone value 0 through 3. A generalized GLCM for that image is shown in figure 1b, where I, j stand for number of times I and j have been neighbor, satisfying the condition stated by displacement vector d. Test image, general form of GLCM. The 4 GLCM for angles equal to 0 degree, 45 degree, 90 degree and 135 degree and radius equal to 1 are shown in figure 2a to 2d. GLCM for delta is equal to 1 and theta is equal to 0 degree. GLCM for delta is equal to 1 and theta is equal to 90 degree. GLCM for theta is equal to 45 degree and delta is equal to 1. GLCM for delta is equal to 1 and theta is equal to 135 degree. Choice of radius delta. Delta value should be ranging from 1 to 10, but the best result is for delta is equal to 1 and 2. Applying large displacement value to a fine texture would yield a GLCM that does not capture detailed textural information. As a pixel is more likely to be correlated to other closely located pixel than the one located far away, the above consideration is correct. Choice of angle theta. Every pixel has 8 neighbors pixels, allowing 8 choices for theta, which are 0 degree, 45 degree, 90 degree, 135 degree, 180 degree, 225 degree, 270 degree and 315 degree. According to the definition of GLCM, the co-occurring pairs obtained by choosing theta equal to 0 degree would be similar to those obtained by choosing theta equal to 180 degree. This concept extends to 0 degree, 45 degree, 90 degree and 135 degree as well. Hence, one has 4 choices to select value of theta. Common statistic derived from co-occurrence probabilities. Energy, also called uniformity or angular second moment. Measure the textural uniformity, that is pixel pair repetitions. Detects disorder in textures. Energy reaches a maximum value equal to 1. Entropy measures the disorder or complexity of an image. The entropy is large when image is not texturally uniform. Complex texture tend to have high entropy. Entropy is strongly but inversely correlated to energy. Contrast measures the spatial frequency of an image and is difference moment of GLCM. It is the difference between the highest and the lowest value of a contiguous set of pixels. It measures the amount of local variations present in the image. Homogeneity, also called as inverse difference moment, measure image homogeneity as it assumes large values for small gray tone difference in pair elements. It is more sensitive to the presence of near diagonal elements in the GLCM. It has maximum value when all the elements in the image are same. Homogeneity decreases if contrast increases while energy is kept constant. Variance. This statistic is a measure of heterogeneity and is strongly correlated to first-order statistical variables such as standard deviation. Variance increases when the gray level value differ from their mean. Variance. Difference entropy. Gray level difference method. Gray level difference method GLDM calculates the gray level difference method probability density function for the given image. This technique is usually used for extracting statistical texture feature for a digital mammogram. The GLDM is based on probability of occurrence that two pixels separated by a specific displacement vector 6 have a given difference. The 5 textural features used in the experiment are contrast, angular, second moment, entropy, mean, and inverse difference moment. In this study, we compute the probability density functions according to 4 kinds of displacement vectors and calculate textural feature for each probability density function. The 4 kinds of displacement vectors are considered as 0, d, minus d, 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 0, d, minus d, where d is inter-sample spacing distance. Run length. It's a simple lossless compression, so it's easy to reconstruct the original image. It consists of idea to encode consecutive pixels by indicating the starting pixel and the run pixel. The output representation is run is equal to row column length. Index starts from 0 in vertical and horizontal direction.